Right, hello grade 12s. This is very, very exciting to me. This is probably my favorite section of the grade 12 syllabus, which is called Differential Calculus. And you'll see also where I have put it on the Google Classroom, it says in exclamation marks, it says the start of Differential Calculus. So I cannot reiterate how important this section is. You really need to concentrate and you need to give me any feedback if there's anything you don't understand, because this is really an important section for paper 1. Along with functions, I would have to say about 40% of your paper 1 is made up of functions and differential calculus. So this is the part where you really can't slack off, you really need to concentrate, you need to do all the exercises and you need to understand everything that we're talking about. So yeah, let's get started. Okay, so very excited. I have Mrs. Smith joining me. So you will, that's Mrs. Smith, you'll hear her voice every now and again. And it's pretty much just so she can keep me honest. So that's the first change. Mrs. Smith is going to keep me honest. So if I make any mistakes, she's going to point them out, hopefully gently. And then the other thing I need to explain as well is you will see, not in this video per se, because this is an introduction, but later on in the differential calculus videos, you'll see I will talk about something called the Lucinda Method. Shout out to Lucinda Landman. And I will also talk about the Joshua Method. Shout out to Joshua Jansen van Ebenezen. Okay, now to explain those two to you, the Lucinda method is very step by step by step. So if I use the Lucinda method, I will say step 1, do this. Step 2, do this. Step 3, do this. Okay, so Lucinda method, that will come in certain sections. And then the other one I will bring in is called the Joshua method. So the Joshua method is, but ma'am, how can they make this more difficult? How can they complicate this? What are the interesting questions they can ask about this? So the Joshua method is, we're about to get a little bit crazy right now. Okay, so blame Joshua for that one. Okay, right. Now, introduction into differential calculus. Now, the first thing I always start off when I talk about differential calculus is differentiation is all about gradients and rates of change. So I always start off by doing something very silly that works very well. I always say to my kids, I say derivatives, you say gradients. Derivatives?
Gradients!
Derivatives?
Gradients!
Thank you to Mrs. Smith. So we'll do that again, and I almost want you at home to do the same thing. So I say derivatives, you say gradients. Derivatives?
Gradients!
Derivatives?
Gradients!
I say gradients, you say derivatives. Gradients?
Derivatives!
Gradients?
Derivatives!
So whenever I talk about differentiation, we are talking about gradients and we are talking about rates of change. So please, people, I will again and again refer back to that. That's the whole purpose of differential calculus, is to calculate gradients and rates of change. So in order to do that, we need to go back a little bit and talk about gradients first. So when we talk about gradients, just remove this little piece of paper because I see it's shining through. When we talk about gradients, you will notice over here, that's the stock standard formula for gradient, where gradient is y2 minus y1 over x2 minus x1. And that is specifically talking about a straight line. So if I have a straight line, and I have 2 points on the straight line, then I will say this is the first point, so x1, y1, and that is the second point, so x2, y2. And then if I find the difference in the y-coordinates divided by the difference in the x-coordinates, that's called gradient. So, I mean, you've been doing this pretty much since grade 8. And we did it in grade 8, we did it in grade 9, we even repeated it in grade 10 and 11 analytical geometry. So you should really be comfortable talking about what the gradient of a straight line is. So just to show you again, it's the change in y over the change in x, and that's written as a ratio. So please guys remember, we're going to refer back to this again and again and again. Right, now I also need to revise another concept that you did briefly in grade 11 functions. And that concept is called average gradients. Now average gradients specifically refers to non-straight line functions. So functions that aren't linear, in other words, functions that when you draw them, they give you a curve. So if I draw a simple curve in there you go, and I put 2 points in there, then what you need to notice is you need to notice that if I draw a straight line that connects those 2 points over here, that is not the actual gradient of the curve. That is what we refer to as the average gradient between these 2 points. So between the first point and the second point, if I draw a straight line, I can work out the average gradient. Now we are going to go and we're going to use some notation. So I need to quickly just talk about notation so it doesn't confuse you. And that notation refers to the fact that we normally call these functions f or g or h. So we're not going to call this the point x1, y1. We're going to call this the point x1, f of x1. Because remember, if I substitute x1 into the function, I get the y coordinate. So that's x1, f of x1, which is exactly the same as saying y1. But we're going to use this notation more often than not. And then that point, if that's the second point, we're going to say that's then the f of x2. So again, that's the notation we're going to be using. And that is why my average gradient, we generally use the formula saying it's the f of x2, which is the same as y2, minus the f of x1 divided by x2 minus x1. So this is the formula we're going to be using whenever we talk about average gradients. So let's do a simple example on average gradients, which, like I said, we did do these examples in grade 11 when we were dealing with functions, but we went very briefly through them, so we do need to just go and revise them to make sure you understand this. So this question says, determine the average gradient of the following curve, and the curve is fx, which is x squared minus 2x minus 15, which, if you know about functions, that's a parabola. And we're going to find the average gradient between 2 points, because looking at this, average gradient always has to be between 2 points. So it's the gradient of that line drawn through the 2 points. So to do this, I'm going to simply go and say, write down the formula that we've just established. The average gradient is equal to then f of 3 minus the f of 2. And that just refers to the y coordinate where x is equal to 3, which means I'm going to substitute that 3 into fx to get the y coordinate where x is equal to 3. And then that f of 2 talks about the y coordinate where x is equal to 2. So again, I'm going to substitute that 2 into that equation to get the y coordinate specifically where x is equal to 2. And then at the bottom, quite easy, the x coordinates, which is just 3 minus 2. Now, by the way, you can do the substitution separately if you want, or you could go and you can do it in the graph. Now, some of you, if I write it all down, you might get a little bit confused. So I'm going to do it separately. I'm just quickly going to go and say, let's work out the f of 3, which is 3 squared minus 2 times 3 minus 15. And that's going to be 9 minus 6 minus 15. So 9 minus 6 minus 15. Mrs. Smith, how's your...
Negative 12.
Negative 12. Let's see. 9 minus 6, 3. Yeah, I'm happy with negative 12. Thank you very much.
My addition is as bad as yours.
Hey, this is not addition. This is mostly multiplication, but okay.
That was adding. 9 minus 6 minus 15 is definitely addition.
This is going to get very interesting, grade 12s. Okay, I might have to actually kick her out of the classroom, but we'll see how it goes.
She won't, you know that.
So first things first. Well, actually second things second. We're going to go 2 squared minus 2 times 2 minus 15. And then we're going to have 4 minus 15. Much easier. That's going to be equal to negative 15. Okay. Now I need to just get a clean piece of paper to continue this. So now we can go and we can sub it into this part right there, which says the average gradient is then equal to f of 3, which we've established is equal to negative 12, which is the y coordinate where x is equal to 3, minus 15, which is f of 2, which we've established is the y coordinate where x is equal to 2. If this confuses you, you can always just go and say, so this is the point 3, negative 12, which is a point on the graph, and this is the point 2, negative 15, which is a point of the graph, and that's pretty much where we're getting that y2 minus y1 divided by x2 minus x1. Right, so simply we're going to go minus 12 plus 15 is equal to 3, and 3 minus 1 is 1, which means my average gradient between these 2 points is then equal to 3. And that's pretty much what average gradient is all about. It just involves a substitution to calculate these y coordinates. And then I substitute the y coordinates to get the difference of the y coordinates. And then I substitute the x coordinates, which by the way was given to you. And I subtract those two to get the difference of the x coordinates. And that's my average gradient. So yes, we are going to refer back later to average gradients. Now, in order to do the work that we're later going to do, we have to establish a formula for average gradient. And we are going to establish this formula in this video, but we're actually only going to use it in the next video, which is where we start talking about something called first principles differentiation. So in order to do first principles differentiation, we have to establish this formula for average gradient. Now, in order to establish this formula, I'm again going to go and just draw a curve, and I'm going to indicate 2 points. And I'm going to draw a line through these 2 points because I want to work out the average gradient between these 2 points. Now let's say this curve is again called the function of f, which means this one is then called x1, f of x1, and this one is then called x2, f of x2. Got it. So we discussed that previously, but now what we're going to do is we're going to adjust this ever so slightly. So look carefully, and I'm going to, this is what the reason why I've drawn it here again, so you can compare the two as I go. So there's my curve again, and there's my first point. Now this point, again just on the function of f, I'm going to call this point just x. But now what I'm going to do, and this is the interesting part that you might not understand initially, but just bear with me. I'm now going to move a horizontal distance of h units to this point. So if I move a horizontal distance of h units from x, this point is going to be the point x plus h. So please note, x is any point on the curve of f. We call it x. And then I move a horizontal distance of h across. So this is the point x plus h, which is just x plus h is x plus h. Now that means this y coordinate is called the f of x, right there. But this y coordinate is then going to be called the f of x plus h. Right. And that's specifically if I move one point to the next point and I move at a distance of h. So logically speaking, in the previous example, we said that distance of h is equal to 1 unit because I wanted to get the average gradient between 2 and 3. So I had 2 there, and then I had to go and say 2 plus 1, so my h there is 1, is equal to 3. And then over there I had the f of 2, so I substituted 2 in there, and then over there I had the f of 2 plus 1, which was the distance between the 2 points, so I had the f of 3 there. So this is pretty much still doing what we were doing before, but you'll see in the next video why it's so important to establish this formula. So I can then go and I can say the average gradient, specifically on this problem, is then going to be y2 minus y1, so it's the f of x plus h minus the f of x, divided by x2 minus x1. But here, careful, x2 is that whole x plus h, and I'm going to subtract from that x. So if I simplify this, I end up with the average gradient being the f of x plus h minus the f of x, and then in the denominator, x minus x eliminates, so I'm left with h. And this is a very, very important deduction, this average gradient. I'm going to put a nice big bubble around that, and we will get back to that in the next video on first principles differentiation. And like I said, it doesn't seem to make a lot of sense at the moment, but as I explained, if I refer back to the previous one, it's just once I know what the distance is between the 2 points, I can use this formula if I know what that horizontal distance is between the first point and the second point. So please, please, please just hold on to this one because I'm going to explain it later, and this is going to become super, super important in the next video. Now, what we need to do now is we need to go off on a little bit of a tangent. My kids will know I just told a horrible joke because we're going to get to tangents later on, especially the AP Maths kids. You might be chuckling right now, and the rest of the kids, you might be thinking, this is weird, which,
Yes, it is.
yes, Mrs. Smith agrees with me, this is weird. But hopefully eventually you'll get the math joke, not now, clearly. Okay, so Now, that little sidetrack we're going to go on today is something called a limit. And this limit, again, guys, it's a plug-in. It's a plug-in into what we call first principles differentiation, which is the next video. So for now, I need to teach you this concept of a limit in order to use it as a plug-in in the next video. So if you're not too clear about this right at the moment, please don't stress too much about it. I will refer to it again in the next video, but I can't use limits in the next video unless you actually know what a limit is. So this is an introduction to limits. Now, if you don't understand my theoretical discussion on limits, please just remember this. A limit, in many instances, is merely a substitution. And especially for core mathematics, that's pretty much the only way we use limits. We use it as an algebraic substitution. So I'll explain to you how it works, but most of the time it's just a substitution. So the way this example reads is it reads like this. It says, evaluate, and that's quite interesting about limits. In a limit, we never say calculate a limit. We always say evaluate a limit. Okay, so evaluate the limit, and it reads like this, of x tending towards 3 in the function x squared minus 6. Now, like I said, I'm going to explain to you just now what it means, but in many instances, people, to calculate this, it merely involves a substitution. So I'm going to go and I'm going to write an equal over here, and in order to calculate this limit, I'm just going to substitute 3 into x. So I'm going to go 3 squared minus 6, which is 9 minus 6, which means the limit is equal to 3. Now, what does this actually mean? What it actually means is if I were to go and draw a parabola, specifically this parabola, and it doesn't have to be accurate, so this is the parabola x squared minus 6. Then, as I approach 3, so let's say for instance 3 is round about over here, I'm guessing, I'm hoping that's correct. But what we're saying is, if I were like a little man walking on this parabola, going towards the number 3. Then over here, I'm going towards the number 3. So that's all that it's saying. It's saying as our x over here, as x approaches 3, the function approaches 3. So that's why I can actually just do a substitution and I can work that out. But again, people, you don't actually need to understand what that limit means. You just need to be able to do it. And in most instances, it just merely involves a substitution. So just substituting. Now, I do want to make a quick comment here, and this is very, very important, about how you write a limit. And in order to do that, I just need to draw a little line over here. So you will see that limit that I wrote above here. I wrote limit of x tending towards 3 of x squared minus 6. Please, people, when you write this in your book with the lines, do not write the limit on the line and write the x tending towards 3 underneath it. That is incorrect. That limit of x tending towards 3 must be in line with the x squared minus 6. They are very pedantic about this at university level. So if you were to write it like this, if I draw the lines over here, and you were to write the limit of x tending towards 3, x squared minus 6, that, people, very, 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 very wrong. You need to write it like this. So please watch the way you write it. Another thing that is very, very common is a lot of people, they put an equal sign in there. Guys, Mrs. Smith is laughing at the moment just because this is so horribly wrong, it's not even funny. You need to understand that a limit, if it doesn't have a function, it means absolutely nothing. So you can't tell me the limit is equal to the function. No, it's the limit of the function. And that is why you will notice very carefully that now later on, you always put the equal sign there if need be. You never put the equal between the limit and the function. The equal sign will go there. So in the next examples, you'll see we're going to use that equal sign in front of the limit, not between the limit and the function. So please, please, people, that notation, incredibly, incredibly important. So let's look at another example. And this is where limits get interesting. And the reason it gets interesting is the following. I told you a limit is merely a substitution. So if I were to go and do a substitution here, and I'm going to do it on the side, if I were to say it's 2 squared minus 4 over, and then at the bottom I go 2 minus 2. Now right there, Right there, people, this is our problem. And the reason this is our problem is because you will notice that 2 minus 2 is equal to 0. Now that means, technically speaking, if this were merely a substitution, I couldn't do it because I get a 0 denominator. But because it's a limit, I am actually allowed to do it. But I have a little trick in how to do it. And that little trick, if you look at the top of the limit, if I go 2 squared minus 4 is also equal to 0. Now I'm going to refer back, and a lot of you guys may not have understood that video that I posted on the factor theorem very clearly, but hopefully you'll understand. If I substitute 2 into the bottom and I get 0, it means x minus 2 is a factor, which clearly it is because that's a linear factor, x minus 2. But if I substitute the 2 into the top, the numerator, and I also get 0, it means that x minus 2 is also a factor at the top. So that means I can now go and look at the way I write it, equals the limit of x tending towards 2, and I can factorize the top saying it's x plus 2 times x minus 2, which is the difference of 2 squares, over x minus 2. And right there you see that common factor of x minus 2 that I was talking about. And that's why you get that 0 over 0 over here. And because of that common factor, I can divide it away, and now, people, I'm allowed to do the substitution. So now I'm allowed to go and say, substitute 2 in there, and by the way, we haven't discussed this yet, but you'll notice I still wrote the limit. Why did I write the limit? Because I haven't done the substitution yet. The moment you do the substitution, you drop that limit. So the moment you substitute x with 2, you say it's 2 plus 2, which gives me an answer of 4. And that's the part where I said, please guys, the equal goes in front of the limit. It doesn't go between the limit and the function, because it's the limit of the function. And as far as I'm doing this algebraic simplification, you are not allowed to drop that limit notation until the substitution is done. Please, people, you do get penalized for notation if you use the notation incorrectly. So we're going to do 2 more examples of these limits. They're very easy and straightforward. You'll see it pretty much involves a factorization, and then it involves a substitution, and then I've got an answer. So let's do the last 2 examples. Next example. Again, if I substitute the -1 in here, you will find that's going to be 0. But if I substitute the -1 into my numerator, you will also find I get 0. So the moment I get that 0 over 0, it means first factorize before you do the substitution. So again, I write the equal over here. I do not drop that limit notation yet because I haven't finished my substitution. So while I'm factorizing, I keep that limit notation, and watch out, equal in front of the limit, not between the limit and the function. Please, please be careful. So I factorize the trinomial saying it's 2x times x, and then this is going to be 3 times 1, and it's minus 3x and minus 3x and plus 2x, which can be that minus x. I factorize the difference of 2 squares, x plus 1, x minus 1, and look at that. I divide that common factor. That, by the way, is again what caused the 0 over 0. Using the factor theorem, you understand 0, 0, and now because I've divided that factor away, I can do the substitution. And the moment I do the substitution, I can now drop that limit notation saying it's 2 times -1 minus 3 over -1 minus 1. And I can simplify that saying this is minus 2 minus 3, which is minus 5, over minus 1, which is minus 2, and then obviously I can finish up by saying it's 5 over 2. So that's exactly how you calculate limits, nothing too complicated. I mean, if you didn't understand my explanation drawing that little graph, it really, really doesn't matter. It pretty much most of the time involves a factorization and then a substitution, and that's how you calculate limits.
I'm going to give Lucinda a heads up. She's going to ask, if we're in class, please can you do the steps?
Yes, Lucinda is going to ask for the steps.
Yes.
You are absolutely right. So, using the Lucinda method, thank you, Mrs. Smith.
See, I've got you, Lucinda.
We're going to first say, to calculate a limit, step 1 is factorize the function if you can. So obviously, sometimes you can't factorize the function, but factorize the function if you can. So we're then going to say it's the limit of h tending towards 0. And then if you notice, we can factorize that. We can take out h as a common factor. So we take out the h, and we're left with 2h minus 4 over h. So step 2 is then going to be simplifying the function. And that pretty much just involves dividing the h by the h. Then I'm left with the limit of h tending towards 0 of 2h minus 4. Notice I haven't dropped that limit notation yet because I haven't actually done my substitution. So my last little step, step 3, is going to be substitute the variable, in this case h, with the value indicated. And that value in this case, h tending towards 0. So I'm going to say 2 times 0 minus 4, which means my final answer is -4. And that, for those of you who are not familiar with it, is called the Lucinda Method. And I will be using this Lucinda Method in quite a few of the videos. There's no Josh method for this particular video because this is still an introduction. It's still very simple, very straightforward, just trying you to understand the concepts. Now, I generally also do a little summary. And this summary, I haven't got a name for it yet, so I thought I will dedicate the summary to Michelle King. So this is going to be the Michelle method. So the Michelle method specifically says, what do I need to know? My checklist at the end of every single video. So I'm going to give you a little checklist. And that checklist, very simple for this one, is you need to understand how to calculate average gradients. You have to be able to calculate an average gradient. That definitely you need to be able to do. Got it. And then you need to be able to evaluate limits. So if I give you a limit, you need to be able to evaluate that limit. And this is pretty much all that I need you to be able to do after you've seen this video. So obviously, if you know I can calculate an average gradient, you can tick that off. And if you can say I can evaluate the limit, you can tick that off. So after this video, this is the goal. And I will be doing this Michelle summary at the end of every single video. So you can then go and you can do your little checklist and you can mark it off. Because like I said, incredibly important section. So I will be with you every single step of the way. Thank you very much for listening, grade 12s.
Bye.